This is the last video for this week. We're going to finish chapter 13 and get started a little bit in chapter 14. Um, let's finish off chapter 13 right now. The other thing that plate tectonics affects is the distribution of life. And when we're talking about life in geology, we're mostly interested in extinct life. Species that used to exist but no longer exist. We're also interested in how species have evolved or changed with time. And plate tectonics can affect the way species change. Just to give you an example, this is straight out of your textbook. Here you have a map. This is South America. This is Central America. West of Central America, we have the Pacific Ocean. East of Central America, we have the Caribbean. You can take a boat or a ship through the Panama Canal to go between the Pacific Ocean and the Caribbean Sea. However, the organisms that live on the Caribbean side cannot get to the Pacific Ocean. They can't go through all the locks of the Panama Canal. They would get crushed. So basically, the organisms that live on the Caribbean side cannot encounter those on the Pacific Ocean side. Therefore, they live in totally different environments. If you take a look at the gastropods and bivalves, and we'll talk a lot more about gastropods and bivalves later, but for now, just when you think of gastropods, think of snails. When you think of bivalves, think about what bi means. It means two, and valve means shells. Think of creatures that have two shells, such as clams, oysters, scallops, mussels. The animal lives inside and has two shells, and they open up their shells on a hinge. If you look at the gastropods and bivalves on the Caribbean side, this is what their shells look like. If you look at the gastropods and bivalves on the Pacific side, this is what they look like. You can clearly see that these gastropods and bivalves look similar but different. Similar but different. For example, this gastropod has a bulge coming out the top, and this one is much flatter. This gastropod has a star-shaped head for the shell, and this one it comes to a point. This type of bivalve on the Caribbean side is smaller, and there's very few gaps between the two shells, whereas this bivalve is much larger on the Pacific side, and it has these two openings. The fact that they look so similar and their DNA is also so similar, it indicates that they had a common ancestor. And this is how plate tectonics affects the evolution of life. Because when did Central America form? It formed 3 million years ago. When North America collided with South America 3 million years ago, a land bridge between South America and North America was formed. And this land bridge is what we call Central America. Panama, Guatemala, Nicaragua, Costa Rica, this area did not exist 3 million years ago. It was formed by the collision between North America and South America 3 million years ago. And so this is a suture zone. It was formed at an ancient continental convergent plate boundary. Bottom line is, 3 million years ago, there was just one type of snail, and one type of this type of snail, and one type of this type of bivalve. But 3 million years ago, when this came together, the snails and bivalves on this side had to adapt to different conditions, and therefore they changed and evolved differently than those on this side. And this shows you how new species are formed. They originally belonged to the same gene pool, and they could mate on both sides. But then you separate the gene pools by putting a landmass between them, and then they're forced to evolve differently because the conditions on both sides are different. And eventually, over time, these organisms become so different they can no longer mate with one another, and they form new species. So plate tectonics can cause new species to evolve when you separate an original species into two groups, one on one side of a land barrier, one on the other side of a land barrier. When you think about plate tectonics, please don't forget that convergent plate boundaries, where you have these black triangles, is where we find ore, metal, precious metals, valuable metal ore deposits such as iron and copper, nickel, gemstones, and even oil and natural gas. Here's the famous Bingham Copper Mine, the largest mine in the world in Utah. Many people, when they drive or fly or take the train to Utah, want to visit the Mormon temples in Salt Lake City. But there's another big tourist attraction in Utah, and that's the Bingham Copper Mine. You can go there. It's about 20 miles from Salt Lake City, and see the largest copper mine in the world. They have train tracks going all the way down to the bottom of this copper mine, and this just shows you, it tells us something quite important, and that is that in the 60s, 70s, and 80s, this mine was very profitable, but they closed it in the 80s because of competition from South America, where they could mine the copper cheaper than us, because the workers who worked at the Bingham Copper Mine had union wages and very high wages, but if you in South America they pay 10, 15 times less, and so there was no way for us to compete. But in the 90s we reopened this mine. How do we do that? How do we keep these high-paying jobs in the United States and at the same time keep our companies profitable? We need to do that. Otherwise, our national deficit's going to get worse off, and the high people will all be forced into low-paying service jobs. We do it through technology. So by building the railroad going down to the bottom of the pit, by building, using machines that can dig up tons of rock very quickly, by using technology to remove gold and silver from trace amounts from the rocks, and so that we can get the gold and silver in addition to the copper, and by developing the technology to purify these metals easily into ingots and bars, we have one worker for every 20 workers there in countries with much lower wages. So we reduce our manpower, but we still are profitable and we still keep the jobs in this country. That's really a good thing, in my opinion. A lot of people they say, oh, we shouldn't do the mining because of the chemicals and the possibility of polluting the environment. I agree that it is important to keep the water supply clean and to keep our environment clean. But to shut down the mining industry would make us dependent on foreign countries. It could be a national security risk during a war if we don't have access to these materials and our own mining operations. Also, we have a huge national deficit, and we need to keep the jobs and in the United States so that we don't send our money overseas, so we keep it here, and that benefits everybody, and we can keep the environment clean at the same time. Let's go into chapter 4 here. Chapter 4 is about geologic time, concepts, and principles. Geologic time is vast. It goes into millions, hundreds of millions, and billions of years. And there are two basic ways in which we date rocks. The first is called absolute dating, which is also called radiometric dating, or some people call it numerical dating. We're just going to call it absolute dating. The second type of dating is called relative dating. Okay, what's the difference? Well, when you're dating rocks or anything, but we're focused on rocks, we want to figure out how old they are. For example, if I pick up a piece of granite, an igneous rock, I want to know how old it is. And if I use radiometric dating, I might be able to figure out, based on how many parent and daughter atoms are in the rock, how many half-lives have gone by. In other words, I can figure out how old it is. So absolute date, I pick up a granite and I find out that piece of granite is between 380 and 382 million years old. That's an absolute date. That's a number. I don't know how old you are, but let's say you're 19 years old. That's a number, and that's an absolute date. Maybe your father is 50 years old, or whatever. Maybe the United States is 245 years old. Germany is 139 years old. It's a number. Relative dating means that something is older than something else. And we learned how to do this in geology before we did absolute dating. So what is relative dating? No, relative dating doesn't mean you go to the family reunion and you go and you look at your cousin and you go, she is beautiful. No, that's not relative dating. And that's not right either, by the way. But relative dating is you are younger than your mother. You are older than your brother. The United States is younger than China. The United States is older than Germany. That's relative dating. So when we're looking at rocks, if we're looking at a whole bunch of different rocks, we want to figure out which rocks are older and which ones are younger for the rocks we're looking at. That's called relative dating. We learned how to do relative dating before we learned how to do absolute dating. I'm going to show you how to do relative dating of rocks, and you're going to do a lab next week on relative dating. Absolute dating came later on, after 1900. In 1900, a great scientist, and her name is, we'll talk about this person. She's a real inspiring person, Madame Marie Curie. And she discovered radioactivity, which would lead for us eventually, by 1907, through another person by the name of Ernest Rutherford, we learned how to date rocks or figure out how old they are. And it is very reliable, ladies and gentlemen. A lot of people say, I don't believe in radiometric dating, but you know, the numbers are solid, and they come from so many different radioactive isotope pairs and so many laboratories, and we always get the same number. That shows that it's a very accurate way of figuring how old rocks are. And we'll talk about the basic chemistry. And don't worry, this is not chemistry class. People worry about that, but we're going to go through it and walk through step by step, and we'll learn about that absolute dating later on. So now you know the difference between relative and absolute dating. Absolute dating is also called numerical dating. In your textbook, they call it numerical dating. You should know the geologic time scale by now, so I'm not going to cover that again. early concepts of geologic time. And James Ussher said the Earth was 6,000 years old, and it was formed on Sunday, October the 23rd, 4004 BC. But I tell you what, James Ussher cannot be right. And James Ussher does not represent Christianity. Most Christians do not believe in a 6,000-year-old Earth. The geologic evidence does not indicate the Earth is 6,000 years old. James Ussher does not represent Christianity. Almost every scientist I know who's a Christian knows that the Earth is not 6,000 years old. And he is one man who lived in the 1600s. He was the Archbishop of the Presbyterian Church. And as you know, England and Scotland joined together with Wales and Northern Ireland to become the United Kingdom. And without getting into all the British history, well, let's just everybody knows who the Henry VIII was and who the Tudor kings were. Henry VIII wanted to know how old King Henry VIII, king of the United Kingdom, wanted to know how old the Earth was. So he asked James Ussher, the Archbishop of the Anglican Church, to figure out how old the Earth was. And James Ussher was the head of the Presbyterian Church, otherwise known as the Church of Scotland. Since Scotland is part of the United Kingdom, he had to do what the king said, which is figure out how old the Earth was. And he looked through the book of Genesis, and he said the Earth was 6,000 years old. But that is not biblical. Almost every Christian scientist I know says that James Ussher's method for figuring out how old the Earth was is flawed, from just in biblical terms, not just scientific terms. By the 18th and 19th century, people already knew the Earth had to be older than 6,000 years old. Two French scientists, Monsieur Buffon and Monsieur Joly, figured out the Earth was... first, Buffon thought the Earth was 75,000 years old, and he based his data on how fast it would take a molten Earth to cool down to form solid rocks. And his number is way off because he did not understand radioactive decay, which produces heat. He didn't understand that there was heat inside the Earth, so his number was much lower. But at least he knew that the Earth was much older. Then Monsieur Joly, he thought that calculated the Earth to be 90 million years old based on how salty the Earth is, how salty the oceans are. And he made his estimate based on how much salt he thought was being added to the oceans and how salty it is now. But that is way off because he did not consider the fact that marine organisms remove salt from the water to make their shells and bones. So, but at least he figured it out that the Earth is much older than 90 million years old was his number. We didn't really get an idea as to how old the Earth was until a Scotsman by the name of James Hutton, a real hero in my eyes, because his theory of uniformitarianism is the foundation of modern geology. And the way James Hutton put it was, James Hutton's principle of uniformitarianism is a two-part theory. And the way he put it was, the first part was, the present is the key to the past. In order to study the past, we must study the present. In other words, if we want to know what the Earth was like 80 million years ago, and let's say we find an 80 million year old quartz sandstone, one of the rocks you looked at in the lab. Well, and let's say we find that quartz sandstone in Jacksboro, Tennessee. Well, that's a record. That quartz sandstone is a record of what environment existed in Jacksboro 80 million years ago. And the way to figure out what that quartz sandstone represents in terms of environment, we simply have to find that same exact type of sandstone forming today and we assume that the laws of chemistry and physics haven't changed over the years, and there's no indication that they have changed, then we can know what Jack's Burrow was like 80 million years ago. So let's say we find 80 million year old quartz sandstone in Jack's Burrow, and it's made of quartz sand. It's well sorted. The particles are all about the same size. They're smooth and round, and they have tiny oyster shells in them. Well, the only place where that can form today is a beach, and that tells us that 80 million years ago, Jack's Burrow was covered by a beach. One more example of James Hutton's principle of uniformitarianism, the present is the key to the past, is this. Let's say we go to north of Norfolk, Virginia. There is a place where you have limestones, and they're filled with coral fossils. Corals are creatures. I don't know if you've ever seen these creatures, but let me show you what they look like. You've seen these if you've gone scuba diving, or if you've gone to Royal Caribbean or Carnival Cruise and gone and scuba diving and seen these beautiful creatures. Well, these are preserved in the rocks, and corals today require 4 things to live: warm water, shallow water, clear water, and sunlit water. The corals only live in warm, shallow, clear, sunlit seas. Therefore, if we find a 380 million year old limestone in Cape Charles, Virginia, we know that 380 million years ago, Cape Charles, Virginia was underneath the ocean in warm, shallow, clear, sunlit seas. Second part of James Hutton's principle of uniformitarianism is that Earth history is unimaginably long. Not tens of millions of years, not hundreds of millions of years old, but even older than that. Another way of putting it is James Hutton said that Earth history is unimaginably long, and the past goes far beyond the eye can see, and the future is beyond the most distant horizon. That's how old the Earth is. Next thing we want to talk about is unconformities. Unconformities. What are unconformities? Well, unconformities are gaps in the rock record where time is not represented. James Hutton was the one who discovered what an unconformity is. And this is the exact place where James Hutton discovered what an unconformity is. It's one of the 3 kinds of unconformities shown here. It's called an angular unconformity. And it's a place located in Scotland at Siccar Point. Here, Hutton noticed you have sedimentary beds, we call sedimentary layers beds, and they are tilting almost vertically. However, on this surface where this geologist in the red jacket is sitting, you see a change. The sedimentary beds are dipping. That means they are tilting, but we say dipping instead in geology. They are dipping, but they're just dipping close to, not too far from the horizontal. So here the beds are dipping like this, almost horizontal, and here they're dipping at a steep angle. What happened here on this surface to cause this change? James Hutton thought about it. And he thought to himself, well, we know that, and this the next thing I'm going to talk about is the principle of original horizontality and the principle of relative dating. No, I'm sorry, of superposition. And these two principles are the first principles of relative dating that we must understand in order to do our lab. The first principle is called the principle of original horizontality. What does that mean? Well, let's take a look at a picture to show you. The principle of original horizontality states that when sediments are deposited, they are deposited in beds, and these beds are horizontal. We know that because when sediment forms in the ocean or in a lake or a river, they're deposited in these horizontal layers. And what that tells us is that if you and I go out and look at sedimentary rocks, and we find that those rocks are not horizontal, such as these beds are not horizontal. We know these beds were originally deposited horizontal, and then they were tilted by earthquakes. And here you can see a stack of sedimentary beds. These were originally deposited horizontal, and then they were tilted. Then what happened? Well, then you've got an unconformity here, because you can see that these beds here are tilted at a different angle. And this unconformity represents missing geologic time. What must have happened is that these rocks were first deposited horizontal. This whole stack of sedimentary beds was deposited horizontal. Then an earthquake tilted them. Then the land was uplifted, like a mountain range uplifted, hundreds or thousands of feet up high, and then these sedimentary rocks were deposited. So this unconformity represents erosion, and the erosion removes layers of rock that are no longer available for us to see. And then another stack of sedimentary rocks was deposited on top. And then another earthquake occurred, and these rocks were tilted. So a geologist could look at this stack of sedimentary rocks and could figure that out. First, this stack of rocks was deposited. This is the oldest, this is the youngest. Because the oldest rocks are always on the bottom for every sedimentary. If you look at a stack of sedimentary beds, the oldest sedimentary beds are on the bottom and the youngest are on top. And that's called the principle of superposition. So, principle of original horizontality, principle of superposition. Let's use that to determine the age of, to determine the historical geology of this outcrop of sedimentary rocks. Okay, let's do it with me and turn the audio off and see if you can do it by yourself to get it down pat. First, these beds here were deposited with the oldest on the bottom, the youngest on top. Then, this stack of sedimentary beds was tilted by an earthquake. Then you had uplift of a mountain uplift. The land was uplifted, and then rocks were eroded away, forming an unconformity. And that's what this surface is, an unconformity. Then this stack of sedimentary rocks was deposited, and another earthquake tilted them. That's the historical geology of the area. And that's your first historical geology example. So, going back to Sicker Point, James Hutton realized that these beds were deposited, then they were tilted by an earthquake. Then a mountain range rose out of the ground, uplift occurred, and then erosion of many of these rocks. So much of the rocks that used to be here were removed. This is an erosional surface, and that these beds on top were later deposited. This is an unconformity. So what James Hutton did was, wow, how much time, no, actually he probably said this, how much time passed by here? These beds are this unconformity, a whole mountain range, and it's colder than a witch's, I'm sorry. But he says these beds were, in order to form this erosional surface, a mountain range had to rise out of the ground. Perhaps thousands of feet had to be of rock or eroded away. And then this other stack of rocks was deposited on top. Another way of saying it, think about it, ladies and gentlemen. This erosional surface might represent more geologic time than this whole stack of rocks. And so that's how Wegener knew the Earth has to be unimaginably long. How much time does it take for a mountain range to rise out of the ground and be worn down flat to form a surface like this? Hundreds of millions of years. Think about it. The Appalachian Mountains are 290 million years old. And they're still here. They're only a third as tall as they were 290 million years ago. It will be another 100 million years before the Appalachians become flat like Kansas is today. So, this erosional surface is an enormous amount of time, and it represents uplifting of the Earth and then erosion of rocks. And that's called an unconformity. I think we'll call it quits here, and next week we'll talk more about relative dating.